Welcome back to Large Language Models. This is Session 5. Last session we saw what attention can do, and it's genuinely remarkable. Give it a sentence, and it finds the relationships between the parts. Which word depends on which, what refers to what. That's exactly what understanding language and context requires, and attention delivers it directly. But there's one thing attention can't do. It has no sense of where a token sits in the sentence. Position is invisible to it. And that's why, last session, we still had to build attention on top of a recurrent network. The RNN was supplying the word order that attention itself has no way to see. Today, let's find out whether we can solve that limitation and throw the recurrence out for good. So let's start with the thing the recurrent network was quietly supplying. Word order. Where exactly does an RNN keep it? Here's the first token, entering the first cell at time step 1. The cell combines what it receives and applies its activation. Now the second token, and notice what arrives with it. A horizontal link from the first cell into the second, carrying the previous hidden state. The second cell doesn't just see cat, it sees cat together with everything the first cell computed. Third token, same pattern. Notice how each cell receives the running summary of everything to its left. And the fourth. Now look at what's carrying the word order here. It's not the tokens, those are just 4 vectors. It's that horizontal chain. Position 1 is whatever went in first, position 2 is whatever went in second. And the only reason the network knows which is which is that it processed them in that sequence, one after another. The order lives in the wiring, and in time. Now let's do the thing this session is about, and cut those horizontal links. Every cell fires at the same instant, because no cell is waiting on the one before it. This is exactly what we want from a GPU. A sentence of n words used to take n sequential steps through the encoder and n more through the decoder, and each of those steps blocked the next. Now they all run at once. This is the question Ashish Vaswani and his colleagues at Google posed in 2017. In the NeurIPS paper, attention is all you need. What happens if we throw the recurrence away and build the whole model out of attention? But something left with those links. Watch the tokens while I shuffle them. Down, sat, cat. A different sentence entirely. And the output is identical. Not similar, identical. With the recurrence gone, nothing in this model distinguishes the cat sat down from down the sat cat. The input is no longer a sequence, it's an unordered set. So we've bought parallelism and paid for it with word order, and that's not a trade we can accept. The next 4 slides solve it. So here's the obvious repair. Hand each cell the one thing it just lost. Give every cell a second input alongside its token, the position. 1, 2, 3, 4. The tokens still run in parallel, nothing waits on anything, and the position is now data the model can read rather than an accident of processing order. Shuffle the tokens and their positions travel with them, so the model can tell the 2 sentences apart. Everything now depends on what we actually put inside those 4 circles. So far, I've just written 1, 2, 3, 4, and that looks harmless enough. Here's a question I'd like you to answer before I do. A short paragraph reaches position 500. A book chapter reaches position 50,000. If the number we feed in is simply the index itself, what breaks? Take a moment with it. There are 3 separate things wrong here, and they're worth finding for yourself before I show you. Let's work through them. The first is a question of size. The numbers already inside a token embedding are small. Values around 0.3, some positive, some negative. Now put the raw index beside them, drawn on the same scale, 512. Watch the bar run straight off the top of the panel. Add that to an embedding, and the position doesn't inform the representation, it obliterates it. Every other feature is noise next to a number 1,000 times larger. The natural repair is to normalize. Divide the index by the sentence length, and everything lands between 0 and 1. Watch what that costs. Here's a 5-token sentence, and the word at index 3 gets 0.6. Here's a 20-token sentence, and the word at index 3, the same absolute position, gets 0.15. The code for third word now depends on how long the sentence happens to be. The model can't learn a stable meaning for a position that keeps changing its name. And here's the property we actually need. which neither attempt has. Take 2 tokens 3 apart near the start of a sentence, and 2 tokens 3 apart near the end. The relationship between them is the same relationship. 3 words apart is 3 words apart, wherever it happens. Whatever we feed in has to keep that recoverable, because how far apart are these 2 tokens is precisely what an attention layer wants to know. 3 failures, and each one is a requirement in disguise. So let's write the specification those 3 failures just handed us. First, bounded. Whatever comes out has to sit in the same numeric range as the embedding values it joins, at position 4 and at position 50,000 alike. A wave does this by construction. It can't leave -1 to +1, however far along you go. Second, length independent. Look at the pair. Position 3 produces the same code in a 5-word sentence and in a 20-word sentence. 0.42 both times. The signal is computed from the position alone, never from the length of what surrounds it. Third, and this is the one that matters most, equal gaps stay recoverable. 2 tokens 3 apart here, 2 tokens 3 apart there, and the model must be able to see that those are the same offset. Here's what satisfies all 3 at once. Not one wave, but a family of them, 1 per embedding dimension, each at its own frequency. Bounded, because they're waves. Length independent, because each value is computed from the position and the dimension index alone, and from nothing else. And relative offsets survive. Sine and cosine have an angle addition identity. Because of it, the encoding at position plus k is always a fixed linear function of the encoding at position. That's a mathematical guarantee. $k positions away is recoverable from the signal itself, at any position. That last property is the one that mattered enough to displace recurrence. This is what the 2017 paper proposed. It has no learned parameters at all, and it has a name. Before we look at the full mathematical picture, let's build the intuition with just 3 positions. That's the whole plan on screen. Pick out 3 positions, pull up the code each one gets, its fingerprint, and compare them side by side. Here's position 3, and here's position 4, right next to it. Look at the pattern of blue and red across the strip. Almost identical. 2 nearby positions produce 2 nearby fingerprints. That's exactly what we want. Neighbors should look like neighbors. Now here's position 40, much farther away in the sentence. Compare its strip to the first 2. A completely different pattern. Distant positions produce genuinely different fingerprints. This is the property from the last slide made visible. Nearby looks similar, far away looks different. And the model can read that difference directly off the signal. Now let's see the full picture at the paper's own scale. Each row is a token position. Each column is a dimension of the embedding space. Blue is a positive value, red is negative, and the intensity is the size of the value. Every row has a unique pattern. No 2 positions look alike. Watch this get written. PE of position 2i equals sine of position over 10,000 to the power 2i over d. Each even dimension is a sine function. Each odd dimension is cosine. The frequency changes with dimension index I. The model can learn to read position from these signals. And it does. So, there's the whole design in one sentence. A family of waves, bounded by construction, computed from position alone, and never repeating. No 2 positions share the same fingerprint. Now we can build up the architecture. Every transformer block, the unit we'll assemble a few slides from now, is built from 2 sublayers, and the first of them is attention. But not just one attention function. Why isn't one enough? Because one attention head learns one kind of relationship at a time. So we run each of them in parallel, each in its own subspace, and each one is free to learn something different. Here's the structure: query, key, and value, the 3 matrices coming from the layer below. Each head receives its own projection of all 3, independently, and produces its own output. And look at what that output actually is. A matrix, a grid of rows and columns. Rows here stand for positions in the sequence. Columns stand for that head's own slice of the dimension. 3 heads shown here, but in practice, the original transformer uses 8, each one its own small matrix. Now the concatenation. The 3 head matrices sit side by side, and together they form one wider matrix. Same number of rows, 3 times as many columns. You can still see the seams, the dashed lines marking where one head's matrix ends and the next begins. That's literally what concatenation is, gluing matrices together along one axis. And then, a real matrix multiplication. The wide concatenated matrix is multiplied by WO, a learned projection matrix, whose row count matches the concatenated matrix's column count exactly. So the multiplication is valid. The result is the output matrix, same number of rows as we started with, but back down to the model's working width. Multi-head attention is a drop-in replacement for single-head attention, but with far more expressive power. Here's the whole mechanism as one line. Multi-head of Q, K, V equals concat of head 1 through head H times W, upper O. That's the mechanism in the abstract. Let's see what it actually does with real numbers. Remember our sentence from session 4. The cat sat. Let's send the query sat through 2 heads and watch them disagree. Head 1 stays local. Look at the numbers. 70% of its attention stays on sat itself, 20% goes to cat, 10% to the. This head is tracking the word in its own immediate neighborhood. Before head 2 appears, take a guess. Same query, same sentence. What different relationship could a second head pick up? Look at head 2. Something completely different with the exact same query. 75% of its attention goes to cat, the subject the verb has to agree with. Only 15% stays on sat itself. This head is tracking subject-verb agreement, a different relationship entirely. Same query, same sentence, 2 genuinely different answers. Concatenate them, and the model holds both relationships at once, and that's exactly what a single head could never give it. Attention gathers context from across the sequence, but gathering isn't processing. We need a second sublayer that actually does something with what attention just gathered. After attention, a small 2-layer network takes each position's enriched representation and processes it independently. And here's the part you should hold on to. The same weights, applied at every position. Here's position 1. It enters as X, is expanded by a linear layer W1, passed through a ReLU, then contracted back by a second linear layer W2. Notice the labels beside each layer. D to 4D on the way in, 4D back to D on the way out. Position 2 goes through exactly the same pipeline, and notice what the labels say. The same W1 and the same W2 at every position in the sequence. No position gets its own private feed-forward network. Here's the whole computation as one line. FFN of X equals the max of 0 and XW1 plus B1 times W2 plus B2. 2 linear layers with a ReLU in between. The inner dimension is typically 4 times the model dimension. A brief expansion that gives the network room to mix features before contracting back. Geva and colleagues showed in 2020 that these feed-forward layers are where the model stores most of its factual knowledge, specific facts learned during training. We now have 2 sublayers, attention and feed-forward. We want to stack many of them, 6 in the original transformer, up to 96 in GPT-3. But deep networks have a well-known problem. Stack enough layers and gradients vanish before they reach the bottom. So here's the fix. A residual connection routes a copy of the input around the sublayer straight into an add step, and now the gradient always has a direct path home. Here's the pattern. The input flows into the sublayer, whatever that sublayer happens to be, attention or feed forward, and a second copy flows around it, along the dashed line, straight into the add. Notice the small tag. This idea didn't originate here. It comes from computer vision. He, Zhang, Ren, and Sun introduced skip connections in 2015 to train very deep image networks in a paper called Deep Residual Learning for Image Recognition. And the insight is simple. Sometimes the best transformation a layer can apply is close to the identity, doing almost nothing. So instead of forcing every layer to relearn that full mapping from scratch, let it learn a small correction on top of identity, and push that correction towards 0 when identity was already good enough. After the add, layer normalization rescales the result, and that's the output. One clean pattern reused everywhere in the transformer. Notice the second tag. Layer normalization is a separate idea with its own origin. Ba, Quiros, and Hinton proposed it in 2016 to stabilize training by rescaling each layer's own activations, one sequence at a time. Earlier normalization methods averaged across a batch of examples instead, which breaks down when sentences stop sharing a length. Together, residual connections and layer norm are what makes stacking dozens of blocks practical. Output equals layer norm of x plus sublayer of x. That's the whole pattern in one line. We've got all the pieces. Let's assemble them. Every encoder block is the same two-step assembly. Multi-head attention gathers context, then the feed-forward network processes it locally. The residual plus norm pattern you just saw wraps both steps. Token embeddings flow in as the input. And notice the small note beside the arrow. Positional encoding was already added before this point. That's the signal from 3 slides ago, still riding along with every embedding. The multi-head self-attention layer is first. After attention, add and norm, exactly the pattern from the last slide. Look at the right edge, its own residual bypass. The feed-forward layer follows, wrapped by the same pattern a second time. That's the complete encoder block. 2 sublayers, 2 residual shortcuts, 1 modular unit that repeats n times. So what's happening in every block is just 2 moves. Gather context, then process it. Each wrapped in the same add and norm pattern. 1 encoder block gives you 1 round of context gathering and local processing. The transformer stacks n of them. Here's the tower. Every block is the same assembly you just built, and each one refines what the block below it produced. And they don't all learn the same kind of thing. The early blocks tend to pick up nearby words and simple syntax, while the deeper ones reach for long-range structure and abstract meaning. Same architecture at every level, different work. And here's how deep this actually goes in practice. Drawn to scale. The original 2017 transformer. 6 blocks. BERT base 12. BERT large 24. GPT-3, 96. Look at the difference between the first bar and the last. Depth is the lever, and pulling that lever is most of what a bigger model has meant. The encoder reads. The decoder generates. And generating, 1 token at a time, requires 2 things the encoder never needed. What are they? First, the decoder must not look at tokens it hasn't generated yet. Second, it needs to attend to the encoder's output. These 2 requirements give the decoder block a 3rd sublayer. The first sublayer is masked self-attention, and this time, look at the small grid drawn inside the box itself, a mask icon. The light cells are positions the query is allowed to see. The dark cells, the upper triangle, are the future, permanently blocked. The decoder generates left to right, and that grid is the mechanism that enforces it. The second sublayer is cross-attention. The queries come from the decoder's own hidden state. But look at the arrow arriving from the left, clearly labeled. The keys and values come from the encoder's output. When the decoder is about to produce cat, cross-attention will concentrate on chat, the French word sitting in the encoder. The encoder doesn't process again. Its output is fixed. The decoder queries it fresh at every step. The third sublayer is the same feed-forward network as in the encoder, local processing after the 2 attention steps. So in plain words, here's the whole decoder block. The encoder block, plus a mask on its own attention, plus 1 extra attention layer that reads the encoder. 3 sublayers, 3 residual connections, 1 decoder block. 3 names have appeared inside the boxes over the last 2 slides. Let's slow down and look at each one directly, side by side. Each of these 3 is the exact same weighted arc mechanism you already know. A query token reaching out to every other token, weighted by relevance. What changes is only the rule for who is allowed to look at whom, and where the keys and values come from. This is self-attention, the encoder's own mechanism. Query, key, and value all come from the same sequence. Look at the arcs. SAT reaches out to every token, including itself, in both directions, forward and backward, with no restriction at all. Now extend the sentence by 1 word. The cat sat down. Watch what happens to the arc, pointing it down. Everywhere else looks the same 3 arcs, just dimmed a little because they're not the new idea here. But the path to down is drawn differently, faint, dashed, marked with a cross. That's masked self-attention. The future is hidden, not by accident, but by a rule built directly into the mechanism. And finally, cross-attention. 2 separate rows now. The encoder's French sentence on top, the decoder's English sentence below. The decoder's query, SAT, reaches up into the encoder row, not sideways into its own row. Queries come from the decoder. Keys and values come from the encoder. Watch where the weight concentrates, mostly on CEST and ASSIS, the French words for sat down. That's the encoder's information crossing over into the decoder, at exactly the moment the decoder needs it. Now, let's see the complete picture, built from the same pieces you've already seen, stacked and connected. On the left, the encoder tower. Input embedding at the bottom, positional encoding added right after it, and then the same self-attention, add and norm, feed forward, add and norm sequence you already know, wrapped in a dashed bracket marked times n. That bracket is the whole repeat unit, the block you studied a few slides ago, stacked n times. On the right, the decoder tower, built the same way. Count the sublayers in its times n bracket. Masked self-attention, cross-attention, feed forward, 3 instead of 2, each followed by add and norm. Above the bracket, a linear layer, then softmax, producing the output probabilities, a distribution over the entire vocabulary at every step. And here's the connection, drawn once as a single representative arrow so it doesn't clutter the page. The encoder's final output feeds into every cross-attention layer of every decoder block. K and V from the encoder, query from the decoder. The bottleneck from session 3, the single compressed vector, is completely gone. 3 properties of this architecture changed what language models could do, and all 3 are easier to see than to say. First, parallelism. On the top row, the recurrent version, 5 cells, 5 steps, each one waiting on the one before it. On the bottom row, the same 5 cells with no chain, 1 step, all at once. That's the trade we made in the first 2 slides of this session, and this is what it bought. Training time drops by orders of magnitude compared to LSTMs. Second, path length. Take the first and last token of a sentence. In the recurrent version, information has to travel through every cell in between, 5 hops, and every hop is a chance for the signal to decay. That's the vanishing gradient over distance that plagued RNNs and even LSTMs. With attention, look at the arc. 1 hop. Any 2 tokens, however far apart, are a single attention step from each other. Distance stopped being a difficulty. Third, scale. The block is uniform and modular, so there are exactly 3 things to grow, and none of them needs a new idea. Stack more blocks, run more heads inside each one, or widen the model dimension. Nothing else changes. That's what made the scaling of the last several years possible, and it's the direct ancestor of BERT, GPT-3, and every major model since. Before we leave the architecture, I want to answer 4 questions that almost everyone has on first contact with that diagram. I had them myself. The first one is about a line that seems to be missing. In most encoder-decoder architectures you've seen, the encoder's output is handed to the decoder as its input, at the bottom, and the decoder reads it from there. That's not what happens here, and it's worth being precise about why. Follow the gold route. The encoder's final output leaves the top of the encoder tower, travels across, and enters the decoder from the side, into the cross-attention sublayer. Not at the bottom, and not once. Into the cross-attention sublayer of every one of the n decoder blocks. And now, the labels make the whole thing precise. Cross-attention takes 3 inputs, like any attention layer. The keys and the values arrive on that gold route. Those are the encoder's output. The query comes up the decoder's own column, from below. So the encoder's output is the decoder's input. It just enters as K and V at every layer, rather than as a starting vector at the bottom. That's the whole answer to the first question. Which raises the second question immediately. If the encoder's output goes in at the side, what goes in at the bottom? The diagram says output embedding, and the sequence we're trying to produce appears as the decoder's input, which sounds circular. It's not circular, and here's why. The input is never the answer. It's the answer so far. At the first step, the input is a single start token, and nothing else. And the decoder predicts one word, the. Now watch the gold arrow. The word we just produced is appended to the input, and the decoder runs again on start the. This time it predicts cat. And again, on start the cat, producing sat. Each row's input is the previous row's output appended. That's what shifted right means on the original diagram. At position I, the decoder sees the tokens up to I-1 and never the token it's being asked to predict. The sequence in the input is what has already been generated, not what we're trying to generate. The third question is about the top of the diagram. The decoder's output is labeled output probabilities, not output tokens. Why does a model that generates text not simply emit the text? Here's what actually happens at the top. The decoder's last layer produces a vector, D numbers, the model's internal representation of the current position. A final linear layer projects that vector from D up to the size of the entire vocabulary. So we get one raw score for every word the model knows. Those raw scores are called logits. Then softmax, exactly the one you met last session. It turns those scores into a probability distribution. Every entry between 0 and 1, the whole set summing to 1. Cat gets 0.62, dog 0.14, and so on across the vocabulary. This is the model's actual output. The token comes after that, and it comes from a separate decision. Take the highest probability entry, which is argmax, and you get deterministic output. Or sample from the distribution, and you get varied output, which is what a temperature setting controls in every model you've used. The model gives you the distribution. Choosing a token from it isn't part of the model at all. The fourth question is the one the diagram never shows: how the model actually runs. It runs in two genuinely different ways, and this is where most confusion about transformers comes from, so stay with me. At training time, we already have the correct answer, so we don't generate one token at a time. The entire target sequence goes in on a single forward pass. Start, the, cat, sat, all at once. This is called teacher forcing because the model is fed the true previous tokens rather than its own predictions. You might be thinking, feeding the model the true tokens sounds like cheating. It would be, except for the grid on the right, the causal mask you met on the decoder block slide. Position 3 can attend to positions 1, 2, and 3, and the dark cells make positions 4 onward unreachable. Every position sees only its own prefix, so no position can read the answer it's about to be asked for. And that's what makes training fast. All 4 predictions are produced on one pass, in parallel, and each one gets its own loss against the true next token. 1 forward pass, 1 backward pass. 4 training signals. This is the parallelism we bought at the start of the session. At inference time, there's no correct answer to feed in, so none of that applies. The tokens produced so far go in, the model runs, and a distribution over the vocabulary comes out. The same distribution we built 2 slides ago. One token is chosen from that distribution and appended to the input, and the whole thing runs again. That's the whole loop, and it really is a loop. The model's own output becomes its next input. This is what autoregressive means. And the loop turns once per token generated. A 100-word answer is 100 full forward passes through every layer of the stack, until the model produces the end token and the loop stops. So training is 1 pass for the whole sequence, and inference is 1 pass per token. Same weights, same architecture, completely different cost, and that asymmetry is behind a great deal of what we'll meet later in this course. The transformer didn't stay one architecture for long. 3 distinct lineages grew out of it, and what separates them is simply which parts of the encoder-decoder stack each one keeps. Let's look at all 3. Here they come. 1 card per lineage. First, encoder only. Take just the encoder stack and you get Bert, Roberta, Albert. Every token attends to every other token, in both directions at once. Excellent at understanding, but they don't generate text. Decoder-only models. GPT, Llama, Claude. These use only the decoder stack with the causal mask. This is the architecture behind the models you use every day. And encoder-decoder models. T5, BART, MT5. Both stacks connected by the cross-attention you've already traced. Translation and summarization are their natural home. Every major LLM today is one of these 3. The next 4 sessions follow each lineage. BERT in session 6, GPT in session 7, then scaling and the model zoo. Let's place ourselves in the 14-session arc. 4 sessions completed. We started with why language is hard, gave words geometry with word vectors, learned to process sequences with RNNs and LSTMs, then broke the distance limit with attention. And today, session 5, we assembled the architecture that ties it all together. the transformer. 9 sessions remain. Session 6 is next. BERT. We've built the engine. We know every component. Next session. What happens when you train one only to understand language? No generation, just comprehension. In today's 2-hour lab, you'll build a transformer encoder block entirely from scratch in PyTorch. No NN transformer encoder layer, no black boxes. Part 1. Implement scaled dot product attention. You can reuse your implementation from the Session 4 lab. Verify the output shape, BTDV. Part 2. Build multi-head attention from scratch. Split QKV into H heads. Run attention on each head independently, concatenate the results, and apply the WO linear projection. This part is where the architecture clicks into place. You'll feel it when the shapes align. Part 3. Assemble the full encoder block. Wrap your multi-head attention and a 2-layer feed-forward network with residual connections and layer norm. Stack 2 complete blocks and verify that the output shape is unchanged. The challenge. Run the same sentence through your encoder block twice. Once with positional encodings added to the input, once without. Compare the output representations. Write your observation as a comment in your notebook. Next session, we'll see why BERT uses learned positional embeddings rather than the fixed sine-cosine version you've just implemented, and what difference it makes.